Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4. We're on chapter 14, which deals with the inorganic carbon complex. And today we'll be starting with carbon dioxide dynamics. So let's get started. Carbon dioxide dynamics. Carbon dioxide gas is a master variable that connects the inorganic and organic carbon cycles through productivity and respiration. Further, dissolved carbon dioxide gas is the major regulator of pH in most inland waters. Finally, partial pressure of carbon dioxide connects surface waters and controls exchange with flux from the atmosphere. Rewriting equation 13-7 reveals an important truth. It is the ratio of CO2 to bicarbonate that regulates the pH of most natural waters for pH values between 5 and 9. So K1 by the concentration of CO2 in water divided by bicarbonate is equal to the concentration of proton. Figure 13-1 gives some of the impression that pH controls the proportions of the species of inorganic carbon. This is not correct in that changing H+ concentration will increase CO2 aqueous in concentration at the expense of bicarbonate concentration. However, in most natural waters, it is in fact the change in CO2 aqueous concentration at relatively constant bicarbonate concentration or constant A and C that actually controls the pH. Increasing CO2 aqueous concentration lowers the pH. Decreasing CO2 concentration in water increases the pH and causes carbonates to form and or precipitate. Since CO2 aqueous concentration is a gas, one might expect that in surface waters that are in contact with the overlying air, partial pressure of CO2 in the air and water would simply be equal. This is not the case. Kling et al. Showed that lakes and rivers in the Arctic were supersaturated with CO2 and a significant regional source of CO2 to the atmosphere. The first extensive global survey of the partial pressure of CO2 in the surface waters from a large number, 1,835 of lakes, showed that only a small proportion were in or near atmospheric equilibrium. Instead, the average partial pressure of dissolved carbon dioxide was about 3 times the value in the overlying atmosphere. Sobek et al. Extended this analysis to more than 4,900 lakes, and Raymond et al. To more than 7,900 lakes and reservoirs, and came to a very similar conclusions. For rivers, the case is even more extreme. Most rivers and streams are quite oversaturated in CO2. These authors assessed a global database of streams and rivers, which included 6,708 sampling locations. They found the average partial pressure of CO2 value was about 3,000 microatmosphere, which is about 7.5-fold greater than equilibrium with the atmosphere. It is not uncommon for many rivers to be supersaturated during the entire year. If partial pressure of CO2 in water is greater than partial pressure of CO2 in the air, the water body is a net source of CO2 to the atmosphere. Thus, on the global scale, lakes, rivers, and streams are on average a net sources of CO2 to the atmosphere, and these sources are significant to the carbon balance of the continents. However, partial pressure of CO2 is quite dynamic in time, and in some systems, and in many systems, it is near equilibrium or consistently undersaturated with respect to the atmosphere, especially in places where primary production is high. It is quite common for a lake to be near equilibrium or slightly undersaturated during the summer and then oversaturated for the rest of the year. On shorter time scales, partial pressure of CO2 in surface waters tends to go up at night and down during the day in response to changes in the balance between primary production and respiration. Over depth, in a stratified lake, as light becomes too low for photosynthesis, partial pressure of CO2 increases as oxygen decreases and accumulates over the course of the stratified period, discussed later. So before we go into that discussed later portion, let's look at these figures. So this is the first figure we are working with here, which is figure 13-2, dissolve CO2 in the surface waters of lakes and rivers lower. So we have rivers here, and then we have lakes here. Relative saturation is the ratio of actual CO2 to the CO2 the water would have if it were in equilibrium with the atmosphere. Lakes with surface waters near atmospheric equilibrium would have relative saturation values of 1.0 on this scale and be on the dotted line. Positive values denote supersaturation, negative values denote undersaturation. A value of 4 means the water body has 4 times as much dissolved CO2 as could be explained by atmospheric equilibrium. -4 means that the water body has 4 times less, or 1/4 as much dissolved CO2 as could be explained by atmospheric equilibrium. So, rivers. So here we have on the y-axis, we have the frequency, so we have the number of rivers that have that values in terms of the relative saturation. And then on the x-axis, we have the value of the relative saturation. So we can see that most of the rivers are oversaturated. So because they are like to the right of that dotted line, and the dotted line would be a value of 1.0, I believe. And then for lakes, we have also most of the lakes on the right side of the curve, but we also have some on the left side. And it appears a little bit more than we do than for the rivers. And so therefore we have maybe, as they were saying in the text, a higher number of lakes that are undersaturated than rivers that are undersaturated. And that makes sense because the rivers, in order for the rivers to be undersaturated, we would have to have very high primary production, and it's difficult for a river to do that because they are flowing water bodies, and so the plants have difficulty settling in and producing CO2 at night, for example, and respiring. Now we have figure 13-3, time series of PCO2 in the surface waters of 2 rivers, the Hudson River near Rhinebeck and the Yangtze River in China. For the Hudson River, we show the partial pressure of CO2 both in the water, field circles, and in the overlying atmosphere. For the Yangtze River, panel B, the wet season is marked with green shading. Okay. So on the y-axis, we have the partial pressure of CO2 in microatmosphere, and then on the x-axis, we have the years. And then here we have the full circles, which are the values of PCO2 in the waters of the Hudson River. And then we have the open circles, the partial pressure of CO2 in the atmosphere. So the first thing that is kind of interesting is there's a fair amount of variability in the partial pressure of CO2, even in the atmosphere itself, even though the variability is not as high than it is in the river, but we do have variability. There does not appear to be a strong seasonality with it, but maybe, like if you see like there's like some peaks here and then some trough there, so maybe some seasonality is kind of hard to tell at that kind of time, that type of scales. Then what we see is that the partial pressure of CO2 in the river is not in sync with the partial pressure in the atmosphere. So the partial pressure in the atmosphere is way lower than it is in the rivers, and we have very high values, even like 5 times what is in the atmosphere, for example, on that data point in 1990, like mid-1998, something to that effect. So this is the Yangtze River, and so we have the same kind of x and y-axis distribution, except for years. We have month here, and we have the wet season that is highlighted in green, and then we have the partial pressure of CO2 in the macro atmosphere. And in this case, I'm assuming that this is basically the variability in the river. We don't have atmospheric values. And during the wet season, we can see that we have higher partial pressure of CO2 in the river itself, and probably due to the increase in primary productivity, algal blooms and the likes. But the Yangtze River is not a river that has a very high flow rates in terms of speed, probably very high volumes, of course, but I think it's a although we would have to verify. It also depends on the location where they took the samples. Maybe this is kind of an area of the Yangtze River where primary production is stronger than other part of the rivers. Then 13-4, we have continuous measurements of partial pressure of CO2 in the surface water of Lake Crush in Quebec. So A is data for a full ice-free season. Points show the mean for the day, and the bars show the range of that day. Okay? And then details, so then B is detail showing several days of partial pressure of CO2 in the same lake along with pH. Note the pH in red dots mirrors the changes in pH CO2. So we actually have seen that before, where we have like the partial pressure of CO2 being the opposite somewhat of the pH. So as the partial pressure of CO2 increases, the pH decreases and becomes more acidic. And we've looked at that in the text. So in terms of the layout of the axis, we have the same on both. We have partial pressure of CO2 in ppm on the y-axis, and then on the x-axis we have time, which in this case we have the month, and it's I believe it would be May through November. And then here we're looking at a time period between like May and July. And so what we see here is we see very high variability, especially in the summer month for intraday variability. So this, as they were saying in the text for the figure, this is the value, the average value for that day, and then this is the range for that day. So we can see pretty big swings in the summer, not as much in the late or in May, but then we see variability, and then it decreases again as we get into the winter season. All right, so of the diverse processes that can lead to CO2 supersaturation, two are the most quantitatively important in the majority of inland waters: importation of CO2 in inflowing surface and groundwater, and two, respiration in excess of gross primary production, often called net heterotrophy. In systems that are supersaturated in CO2 and have very long residence times or high metabolism compared to residence times such as Lake Superior, Lake Biwa, the lower Amazon, or the Hudson River, the excess CO2 is largely the result of net heterotrophy. In systems with short residence times, such as headwater streams, the excess CO2 comes from groundwater. In recent years, a number of attempts have been made to quantify the sources of CO2 efflux in small lakes. There's a remarkable degree of consensus between the studies showing that both net heterotrophy and hydrologic input contribute to the efflux of CO2 from inland waters to the atmosphere. During the ice-free season, many small lakes are net heterotrophic. However, this net heterotrophy is insufficient to account for all of the CO2 efflux. Wilkinson and collaborators found that about half the summertime efflux of CO2 from 3 small seepage lakes in Wisconsin was supported by net heterotrophy, with the remaining 50% from groundwater input. Vacan et al. Showed that for 3 lakes in Quebec, the contribution to lake CO2 emissions varied with season. In the spring, after ice out, CO2 from apolimnetic buildup, for example, net heterotrophy, was the major contributor, 50 to 100%. In summer, 34 to 80% of the flux was the result of respiration in excess of CO2 in the benthos and pelagic parts of the lakes. In fall, hydrologic inputs accounted for 39 to 55% of the flux. Measurement and calculation of PCO2. Like DIC, PCO2 can be measured directly or calculated from temperature, pH, and DIC or ANC. The calculation is highly sensitive to the pH. In dilute waters with circumneutral pH, a great deal of care is required to obtain an accurate pH value. In fact, one might do better by measuring both DIC and PCO2 and calculating the pH. Nevertheless, if an accurate pH value can be measured, calculating PCO2 works well. Discrete measurements options, including headspace equilibration, so let's make sure I'm not missing any text here. Yeah. Discrete measurement options, including headspace equilibration in a sealed container, and then measurements of CO2 via gas chromatography or infrared gas analyzer. The idea in a headspace equilibration is to add a small volume of gas to a sealed container and force by shaking the dissolved gas to equilibrate with that headspace. If the water volume is extremely large compared to the headspace gas volume, the gas concentration in the headspace is a direct measure of the partial pressure. Of course, care is required to maintain environmental temperature or correct for changes. Further, the larger the water volume is compared to the headspace volume, the closer this approach comes to a direct measurement. Calculations are always required to correct for the displaced inorganic carbon equilibrium during the headspace equilibration process. Over the past few decades, it has become possible to measure partial pressure of CO2 directly and continuously using in situ equilibrators and an IRGA mounted on a raft, or an infrared CO2 probe. Continuous record of PCO2 as shown for a full ice-free season in Lake Crush in figure 13.4a. In this lake, PCO2 is consistently elevated above the value of atmospheric equilibrium, and the lake is a net source of CO2 to the atmosphere. A several-day period on the same lake is shown in figure 13-4b. Note that how CO2 goes up at night and down during daylight due to change in the balance between primary production and respiration. Similarly, partial pressure of CO2 increases over depth, as does DIC. Let's review figure 13-5, depth profiles from 3 stratified lakes. A. Lake Crush is a softwater oligotrophic lake. B. Black Pond is a softwater oligomictic, possibly meromictic lake. In this plot, concentrations of CO2 and bicarbonate are stacked. And C. Lake Mendota, a hot water eutrophic lake. All 3 lakes show dissolved CO2 blue dots and dissolved oxygen red dots. We also show the concentration of bicarbonate orange dots for Black Pond shaded area and Lake Mendota separate subpanels. Note the scale break for Lake Mendota in bicarbonate concentrations. Y-axis depth in meters. X-axis concentration in micromoles per liter. For oxygen, CO2, and bicarbonate. Blue is CO2 or carbon dioxide. Orange is bicarbonate. Red is oxygen. So for Lake Crush, we see pretty low concentration of CO2 up to like 5 meters or 4.75 meters, something to that effect, and then an increase in CO2. The opposite is true for bicarbonate. We have higher concentration at the surface, and as CO2 increases, bicarbonate increases, and bicarbonate decreases, except for this area where we have like a bump in bicarbonate. Now for Black Pond, which might be a meromictic lake, but it's at least an oligomictic lake, so meaning by that it doesn't turn over that often. We have concentration of CO2 increasing consistently with depth, and then we have bicarbonate concentration decreasing as well consistently with depth. And then oxygen is also mirroring the concentration of CO2, although oxygen concentration higher in micromoles than concentration of CO2. And here we have Lake Mendota, which is a eutrophic lake, and so that we have CO2 concentration increasing with depth, we have bicarbonate decreasing with depth, so, and then we have oxygen concentration somewhat mirroring the concentration of CO2, but with more of a like a different three regime. We have this regime here where it's constant, then we have this regime where the concentration is increasing at a higher rate than at this point here. And so we may have like a chemocline maybe right here for that lake, and that lake being eutrophic has very high primary productivity, and in all the lakes we see CO2 concentration with depth, and which appears to be consistent with the fact that primary production would increase with depth. As you reach the bottom of the lake, you reach the primary production area with the aquatic plants being able to produce oxygen and respire CO2 at night. So this is kind of a pattern that we see. And then, of course, we see the bicarbonate acting as a buffering capacity with increasing in CO2 concentration in order to alleviate the decrease in pH that CO2 will impart, so that the pH remains stable within the lake. And I think that's about it for the interpretation of this figure, and we'll pick it up tomorrow with subsection D, CO2 exchange between the atmosphere and water. And thanks for attending today's session, and I'll see you tomorrow. Bye.